Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at where does water occur on our planet. So we're going to begin by thinking about where did the Earth's water come from and where is it located today. So the origin of the Earth's water goes all the way back to the material that came together to actually form planet Earth. So the Earth itself formed from pieces of rocky material and icy material that were orbiting the juvenile sun, and they began to come together and coalesce to form the planet Earth. Now, these pieces of material coalescing together ended up producing a lot of heat, and this heat came from the force of pieces of material banging into each other, but also the decay of radioactive isotopes within those pieces of material. And so what happened was when all this material came together, you ended up forming a magma ocean. So there was a time when the Earth was nothing but a sphere of magma. Now, during this period of time, because of the high temperatures and the fact that the Earth didn't have an atmosphere, a lot of the water was actually lost to space. So you're probably thinking, well, where does all the water come from that we have now? Well, it just so happens that around 4 billion years ago, the orbits of Jupiter, Saturn, Neptune, and Uranus shifted slightly, and it disturbed a whole load of comets which are found in an area which we refer to as the Kuiper Belt. And so all of these comets started getting thrown into the inner solar system, where a lot of them hit the Earth and a lot of them also hit the Moon. And so these comets are made up mostly of ice. And so all of this material was added to the Earth, and it helped to essentially add water back into the Earth that had been lost to space. And so this is where a lot of the Earth's water actually comes from. It's part of this late heavy bombardment. Okay, so now let's begin thinking about where the Earth's water is located. So, a very significant portion of the Earth's water is located in the oceans, where it occurs as saline water, also referred to as salt water. So, the oceans contain about 96.5% of all known water on planet Earth. And so this means there's about 3.5% of water which is outstanding, and this occurs as fresh water. And the fresh water is going to be located on the continents and within the Earth's atmosphere. So let's think about how that fresh water is split up. So a very significant portion of fresh water, 69% of it, is located as ice and snow in the form of glaciers and ice caps. Now, there's also a small amount which occurs as permafrost and ground ice, but they are relatively minor when compared to the sheer volume of water contained in glaciers and ice caps. So straight away, we have accounted for over 2/3 of all the fresh water. Now, 30% of the fresh water is contained as groundwater. And groundwater is fresh water which is located in the subsurface, in the pores of rocks, and in fractures in rocks. Now, the vast majority of this groundwater is fresh water. However, as you move towards the coast, it does tend to become more saline, more salty. And that's because you are dealing with a porous layer of rock. And so, just as long as fresh water can move along it, well, it also means that seawater can move along it as well. So as you approach the coast, some of that seawater will begin to infiltrate your porous layer of rock, where it will mix with the fresh water, the groundwater, and you'll end up producing a kind of brackish, kind of slightly salty water as a result. And then as you move even closer towards the coast, the amount of contamination from seawater gets higher and higher, and the water gets saltier and saltier. Okay. So, in terms of groundwater, that accounts for 30%. So, you can see that with a combination of glaciers, ice caps, and groundwater, we've accounted for 99% of all fresh water. So, how is that remaining 1% split up? Well, let's begin by looking at the atmosphere and the soils. So, both the atmosphere and soils contain approximately 0.001% of known fresh water. And you might be slightly surprised by this because when you think about the atmosphere, especially, you think about something that's very, very water rich. So, if you've ever lived in the tropics or if you've ever been in an area that's experiencing a hurricane or a typhoon, you will know that huge quantities of water can be essentially deposited from the atmosphere over very short periods of time. So the idea that it only contains 0.001% of fresh water is a little surprising. However, what you have to bear in mind is that water actually only makes up a relatively small proportion of the Earth's atmosphere. And so, even though it's there in large quantities, because the atmosphere is large, it's not actually not that greater of a portion of the total atmospheric composition. Now, in terms of the water that's in the atmosphere, it occurs as water vapor, water droplets, and precipitation. So the water vapor is just molecules of water which are just floating around in the atmosphere with all the other gases. In the case of water droplets and ice crystals as well, what you have is a situation where that water vapor begins to condense to form droplets or ice crystals. Now, in the case of water droplets and ice crystals, they are light enough that they can be suspended in the air without falling to Earth. And it's these water droplets and ice crystals that form the clouds that we can see in the sky. Now, once the water droplets or ice crystals become too big, they will weigh too much to be supported by the air, and at that point they will fall under gravity towards the Earth's surface, and obviously that's referred to as precipitation. And so precipitation is considered to be part of the amount of water in the atmosphere because the precipitation is obviously moving through the atmosphere on its way to the surface. Now, in the case of soils, you are looking once again at about 0.001% of known fresh water occurring in soils. And it occurs as both liquid water in the soils and it occurs in minerals. So it's split between two main sources. Now, once again, you might think, well, soils, a lot of it around, you would have thought it would contain more fresh water. However, when you think about it in terms of the total size of the Earth, and especially the surface of the Earth, the amount of soil is actually very minimal. The soil is just the finest of fine veneers around the surface of the Earth. So even though soil is pretty much everywhere, and yes, some soil is extremely water rich, the actual amount of water in total which is stored in soils is actually quite low at about 0.001% of fresh water. So in terms of the water that's contained within soils, a lot of that obviously gets removed from the soils by plants, and then obviously those plants will be consumed by animals. Now, to be clear, the water will then be recharged in the soil whenever it rains. So the amount of water which is contained within biological organisms is also an important reservoir. So in terms of biological water, it's contained within the cells of plants and animals. Now, plants and animals are extraordinarily important for surface processes. We have, humans especially have a very serious effect on the Earth's surface. So do plants. The growth of plants helps to accelerate the process of weathering. So plants and animals are very important, and life is very, very common on the surface of the Earth. And so obviously you would once again assume it would be quite a reasonably sized reservoir of fresh water. However, the amount of total water, so we're not talking about just fresh water here, we're talking about all the water on Earth, that's contained within biological organisms is 0.001% of all the water, known water, on the Earth. So once again, it's an absolutely tiny proportion. So even though life is everywhere, when it really comes down to it, it's only a very, very small amount of, the total Earth when you think about it. So in terms of that 1% of fresh water that we know about, well, that's left over, 87% of it actually occurs in lakes. And that's where by far and away the majority of this 1% of fresh water is located. Now, lakes themselves, we find them everywhere. We find them in both cold climates, temperate climates, and warm climates. The ones in warmer climates do tend to be prone to evaporation, and this can obviously lead to the salinities of the water within those lakes getting higher, because obviously as you lose water to the atmosphere, the dissolved minerals which are in the water are left behind, and so that means over time your lake will become more and more saline. And so a good example of this would be the Dead Sea. This is a lake which in a very dry, arid area, so lots of evaporation, not a lot of water coming in, and so slowly over time the water has been getting more and more saline. Now, like I said, the majority of that remaining 1% of fresh water occurs in lakes, but there's also a significant amount, about 11%, which occurs in swamps and wetlands. So these are normally located more towards the Earth's coasts, and they contain a mixture of both waterlogged soil and a lot of organic material. And that organic material is in the form of plants which are alive, but also organic material that has fallen into the swampy environment and, in theory, could later go on to form coal. So there's a lot of water in these areas, and the swamps and wetlands that occur towards the coast, once again, we tend to get this mixing of fresh water and salt water, and that leads to more brackish waters, so slightly saltier water forming. So straight away you can see that a very, very significant amount of that remaining 1% of water is located in lakes, swamps, and wetlands. Now, what's left? Rivers, streams. So rivers contain a relatively small amount of that 1%, about 2% of known fresh water occurs in streams. So about 2% of that 1% occurs in streams. However, streams are very, very important to geology. I mean, the movement of rivers is a significant remodeler of the Earth's surface. As rivers move from side to side and they cut up or deposit sediment, they have a very serious effect on the Earth's surface. And of course, rivers are important for moving sediment off the continents and into the oceans. Now, in terms of the rivers themselves, they actually have quite an oversized importance to society, because rivers are a very simple way of getting drinking water, they're a simple way of getting fish, and of course they are very important for transportation. If you want to get materials from the coast inland, going up a river is always a very important way of doing that. So between lakes, swamps, wetlands, and streams, i.e. rivers, you can see that the majority of this 1% of fresh water has now been accounted for. Now, this then brings us on to another question. You might have noticed that I keep saying known water. Well, that's because we know there's going to be water in the Earth's mantle and in the Earth's crust, and this is going to be contained primarily in minerals. And so the question becomes, well, exactly how much water is located in the Earth's mantle and in the Earth's crust? And it's a bit of a difficult question to answer. Based on the estimates that we have, we believe that the mantle probably contains somewhere around the same amount of water as the Earth's ocean. So we believe there's a significant amount of water in the Earth's mantle. Now, in terms of the crust, we think that it contains about 3% of the Earth's total water, so about equivalent to the amount of water that occurs as fresh water. So when you think about it, the amount of water contained in the crust and in the mantle is about equivalent to the amount of known water that we can see on the surface of the Earth. So there is a significant amount of water in the Earth's deep interior, which we can't access, but we know it's there because we have samples and we can measure its presence, or at least that it was there or has acted on the rocks at some point. Okay, so this diagram here helps to summarize what we were talking about. So as you can see, in terms of the Earth's total water, we have about 96.5% in the oceans and about 3.5% as fresh water. Now, in terms of the fresh water, the breakdown is we have about 85.5% in ice caps and glaciers, 30% in groundwater, and we have about 1% in other sources. And in terms of these other sources, we are looking at streams, swamps, and lakes as the primary host for that remaining 1% of fresh water. So in terms of the columns themselves, the middle and the right-hand columns represent the breakdown of fresh water. The percentages displayed do not include the estimated water contained in the crust and mantle. So, as mentioned in the previous slide, the amount of water that might be contained in the Earth's mantle and crust is equivalent to the amount of water in this column right here, with about the same amount of water in the oceans being in the mantle, and approximately the same amount of water which occurs as fresh water occurring in the crust. So in terms of the estimates, they suggest that the amount of water in the mantle, like I say, is equivalent to the oceans, and the amount of water in the crust is equivalent to the total amount of fresh water that we know about. Now, in terms of, once again, can we actually access this water? The answer is no. So the water that's in the crust and mantle is typically locked in minerals. So as part of the mineral structure, you have water in there, and obviously that water can't escape unless the mineral breaks down. Now, in terms of the water that does exist in the crust and in the deeper crust, there is some water within fractures in those areas. So if you ever go down into the gold mines of the Witwatersrand in South Africa, that's going to take you down about 3 to 4 kilometers down into the earth, so very deep. And in that environment, you are going to see that there is still some water within those rocks, even though the rocks themselves are under tremendous pressure because there's so much material above them. You would think that all that pressure would cause the fractures and the pores to close up, but they don't. And the problem is when you analyze this water, it's often very, very saline, so very salty, and it typically contains significant amounts of dissolved ions, especially iron. And so the water itself in the deeper crust, once again, it's not really useful to humans. In theory, we could access it if you were willing to drill down 3 or 4 kilometers, but the quality of the water is so low that it's just not really worth it. So when we're thinking about water which is used by society, we are just thinking about the water which is accessible in the surface of the earth, and it's this 3.5% up here which occurs as fresh water. So so the next thing we need to think about is, how does the water move between settings on the Earth's surface? And so you might already be familiar with this diagram. This is the hydrologic cycle. So this is going to take us through the steps of obviously evaporation, precipitation, infiltration into the earth, and then a return of that water back to the ocean to allow the cycle to keep constantly repeating itself. So in terms of evaporation, we are going to have water on the surface of the earth, which is going to undergo evaporation. And this evaporation is going to occur due to energy being imparted onto the surface of the earth from the sun. And this energy, primarily seen in the form of light, but also warmth, is going to cause water molecules to vibrate faster. Because increasing energy causes molecules to vibrate faster. If you heat up a piece of metal, the atoms within that piece of metal begin to vibrate faster because of the heat you've put in, the added energy that you're putting in. And so this energy coming from the sun in the form of sunlight and heat, that causes water molecules on the surface of the oceans and on lakes to begin to vibrate faster. And in some cases, they will vibrate with enough force that it will actually break the intermolecular forces that hold the molecules together. And so once those bonds are broken, that water molecule is now free to exit and go up into the atmosphere. And obviously this is now going to occur as free water in the form of water vapor. Now, in terms of evaporation, unsurprisingly, most of the evaporation comes from the ocean. And this isn't a shock because the ocean is a very significant proportion of the Earth's surface. Now, once that water is in the atmosphere, it's obviously then going to be moved around by currents in the atmosphere. But eventually that air is going to enter an area where it's going to cause the water vapor within the air to begin to condense. So in terms of this process of condensation, what's going on? So what typically happens is the air, which contains the water vapor, will begin to be exposed to decreasing temperatures. Now, this could be due to a couple of reasons. It could simply be because the air gets pushed higher, and that might be because as the air is moving along, it hits a mountain range. And so obviously as the air hits this elevated terrain, it has to go up to go over the top of it. And as it goes up, of course, it gets higher in the atmosphere, temperatures get lower. And as those temperatures drop, it encourages the water vapor to come out of the air and it will begin to coalesce, to condense, to form droplets. Now, another possibility is that your air is just happily moving along with the water vapor contained within it, and then it happens to intersect another stream of air. But this stream of air is relatively cold, and where these two streams of air hit each other, they mix, and you essentially have this wetter, warm air meeting this colder air, and once again, where the two bodies of air hit each other, you are going to get condensation taking place. You're going to get water leaving the atmosphere and turning into water droplets. To be clear, these water droplets are suspended in the atmosphere. They aren't falling out of it, but they are forming. Now, in most cases where you have the air cooling, what you will get is water vapor leaves the air and it forms these little droplets of liquid, which we refer to as water droplets. However, if the air is exposed to very cold temperatures, the water vapor might just exit the air and turn directly into ice crystals. Now, to be clear, once again, these water droplets and ice crystals are suspended in the atmosphere. They aren't going to drop out, and they are the main material that forms the clouds that we see in the sky. So what happens next? Well, if the air keeps getting cooler, well, you're going to see the water molecules will begin to become less and less energetic because there's less energy around because of the colder temperatures. And this will encourage even more water to exit the atmosphere and essentially begin to add itself to either the ice crystals or to these water droplets. And eventually the water droplets or ice crystals are going to become so heavy that the air is no longer capable of supporting them. And at this point, once they can no longer be supported by the air, they are transitioning from water droplets or ice crystals, and at that point they become rain and snow. And so once they're heavy enough, gravity will kick in, gravity will take an effect, and it will start to allow these heavier water droplets to turn into precipitation and fall from the sky towards the Earth's surface. Now, in terms of the precipitation itself, quite a lot of precipitation, as it falls towards the Earth's surface, it will begin to drop down into layers of air which are warmer. And so a relatively significant amount of precipitation actually never makes it to the Earth's surface, because as it's falling, it actually starts to evaporate again as it enters warmer air. And so it starts to turn back into water vapor. But that won't happen to all of it. There will be some of that precipitation that makes it all the way to the Earth's surface, and at that point it's going to want to infiltrate, to move into the soil. In the case of snow, well, that will primarily fall in colder, maybe more elevated terrains, and the snow will often be compacted over time as more snow falls on top of it, and that gets turned into ice, where it gets locked in glaciers and ice caps. But where liquid water tends to form is going to be in these areas here, which we can see in the diagram as the greener areas. And in these more temperate conditions, you're going to have the water hitting the ground, and it's going to move either into soil or it's going to move into lakes and rivers. So let's begin by thinking about the water that's moving into soil. Well, this process of water making its way from the surface down into the soil is referred to as infiltration. And infiltration will continue so that the water will actually move through the soil, and then it will actually start to move through the rock underneath. And if it moves deep enough, that water will make it all the way down into the groundwater, this store of water which is located beneath the Earth's surface. Now, some of that water will not exit the soil, it will remain in the soil, and of course that is the water that will then be used by plants. So in terms of this water that manages to pass through the soil and into the underlying rock, this is going to become our groundwater. And once again, groundwater is located in the subsurface, so it's beneath the Earth's surface. And groundwater will actually flow, just like a river. It will move underground along porous layers of rock. And it will tend to move from higher topography areas to lower topography areas. So if we look at our diagram here, we can see here we have an area right there where we have slightly elevated topography. Well, in this case, you can see the topography is dropping off. And so the groundwater is going to follow our porous layer of rock, and it's simply going to go downhill under gravity. And so this movement of water along these porous layers of rock is referred to as groundwater flow. And the bodies of rock through which this water is moving are referred to as aquifers. Now, in the event that one of these aquifers intersects the surface of the Earth, what's going to happen? Well, you've got a layer of rock that's full of water. It's going to essentially come out on the side of a hill, for instance. And so, well, that water's got to go somewhere. It's got to exit the layer of rock, and it's going to do just that. And it's going to end up forming features like springs or lakes, or maybe even streams, i.e. rivers. So the interesting thing about this groundwater flow when it comes out onto the Earth's surface, well, it's a constant flow of water that's coming from a reservoir, essentially. So it isn't actually affected by what's going on the surface of the Earth. And so what you tend to see is in some places, which can be very hot and very arid, and there's no surface water moving around. A good example would be somewhere like the Sahara. Well, you can actually get these locations where you do have water coming to the surface. We refer to them as oases. And the formation of a desert oasis is simply the result of a porous body of rock which contains groundwater, and that water is moving along this porous layer of rock, this aquifer, and the aquifer happens to intersect the Earth's surface, maybe in a dip in the terrain. And so that water exits the layer of rock and it pours out onto the Earth's surface, and it forms essentially a small body of water which we refer to as an oasis. So springs, lakes, and streams can all be fed by groundwater coming out onto the Earth's surface. And so if we look at our diagram here, you can see a situation, for instance, where the groundwater that's coming down from up here may help to go into this lake here and keep it going. And the nice thing about this groundwater flow is that it will actually keep lakes and rivers going, alive, full of water, even during times of year when things can get quite dry. So the next thing we're going to think about is we're going to go back to that water that's located in the soil. Well, obviously that water that's located in the soil, some of it's going to be picked up by plants through their root systems, and so that water is going to enter the plants. Now, the thing about plants is plants have pores in their leaves, just like humans have pores in their skin. And so some of that water that's contained within the plant will actually exit the plant through these pores in the leaves, and it will be lost to the atmosphere through evaporation. So this process of water leaving the plant, primarily through the pores of its leaves, is referred to as transpiration. And this is also going to put water back into the Earth's atmosphere. Now, there's a technical term here. So the combination of transpiration, so that's water leaving plants, and evaporation from the land is referred to as evapotranspiration. And so you add those two together and that gives you a number, and that's the amount of evapotranspiration for a given area. Now, in the event that the ground surface is impermeable when the rain hits the ground, so let's say it hits some concrete, or the ground is waterlogged. So let's say earlier on there were several very heavy rainstorms, and so the soil that the rainwater is landing on is already completely saturated with water. It's full of it. You can't squeeze any more in there. So what's going to happen in that situation? Well, in that situation, because the water can't infiltrate down into the soil, it's simply got to flow across the Earth's surface. And it will move with topography. It'll go from the highest point to the lowest point. And so what it will tend to do is it will move towards rivers and lakes, because rivers and lakes tend to be located in topographic lows. And the movement of this water across the Earth's surface is referred to as surface runoff. Now, in terms of all of this water that falls onto the land, what's going to happen to it in the end? Well, the vast majority of it is going to make it all the way back to the ocean, where it will evaporate again, it will re-enter the atmosphere, and the cycle will continue. And so this obviously is going to be the complete hydrologic cycle. You've gone from evaporation in the oceans into condensation to form clouds, which eventually form precipitation. That water then falls onto the Earth's surface. It can either enter the subsurface and become groundwater, or it can move across the surface as surface runoff. In both cases, surface runoff and groundwater, eventually it will simply make its way back to the oceans where it will evaporate again, and once again, the cycle continues. All right, thank you for watching.